Good afternoon. I'm Talita Persiano. I'm from the Computational Research Division at the Lawrence Berkeley National Laboratory, and I'll be presenting the paper entitled Shared Memory Parallel Probabilistic Graphical Modeling Optimization, Comparison of Threads, OpenMP, and Data Parallel Primitives. So first of all, I would like to explain the problem that we're trying to solve here in this paper, which is the segmentation of three-dimensional scientific images. In our case, we're using 3D volumes obtained using microtomography, and this is a material sample. So the first image here is a two-dimensional slice from one of those 3D volumes, and you can see that there are rock samples or rock structures here. There are represented by lighter pixel intensity values. And also you can see the background that are represented by darker pixel intensity values. So the first step we go through here is called oversegmentation, which aims to create a partitioning of the image into different regions. And finally, from this oversegmentation, we obtain the final segmentation result. In our case, we are obtaining a 2D, a binary segmentation result. So the main contributions of this paper are the introduction of three different implementations of a Markov random field optimization algorithm using C++11 threads, OpenMP, and DPP, data parallel primitives. For the DPP version, we are using the VTKM library. So we also do an in-depth study of shared memory parallel performance of the three different implementations. And we go beyond just doing, for example, performance scalability. We also do an in-depth analysis of hardware performance counters on different platforms. One of the main findings of this study is that the DPP implementation shows much better runtime, but also is the one that has less favorable scaling characteristics. And we're going to go through the details of the analysis that we did to reach that conclusion. So there are several motivations behind this work. The main motivation is that image segmentation is an essential step in several image analysis pipelines. It is a computationally intensive task, especially if you're dealing with big image data, such as the ones obtained by experiments using advanced instruments used at the Advanced Light Source at the Berkeley Lab. Also, there is a high demand of image analysis tools that perform well on modern platforms, and they are expected to be portable to next generation hardware. Finally, Markov random fields can be broadly applied to several other image analysis problems, such as image denoising, feature tracking, texture analysis, and so on. So what I mean by that is that the framework that I'm presenting here can be extended and applied to all these other different image analysis problems. So this slide shows a general diagram of the framework that we're implementing here. So from the original image, we go through a feature extraction step. And from this feature extraction, we obtain features such as pixels, regions, or edges. In the case of this work, we're using regions because we're running the oversegmentation algorithm. From those features, we construct a graph, and we also define a Markov random field model based on that graph. And then we deal with a graph labeling problem. And this is the optimization step of this framework. So for the optimization step, that's the part that we are parallelizing. And the way we do that is through a graph partitioning process. So from the general graph, we use an algorithm called linear and parallel. That algorithm was introduced by Yariv Mizrahi. At that time, he was in the University of British Columbia in Canada. And he introduced the mathematical background to propose a graph partition algorithm that enables the parallelization of probabilistic graphical model optimization. And that's the algorithm that we're using. So from the graph, we obtain several subgraphs, and we optimize the subgraphs separately and in parallel, which means that instead of having one MRF model, we have several sub-MRF models. So once the optimization process is done for all the subgraphs, the results are combined, and then we obtain the final segmentation result. In regards to the oversegmentation step that we use, and then to construct the graph, here's an illustration on how we do that. So suppose that you have this oversegmentation result here. So each region of the oversegmentation is going to be represented by a node of the graph, and two nodes are going to be connected if those two regions are neighbors in the oversegmentation. So for example, if we take a look at regions 7 and 9 here in the oversegmentation, we have nodes 7 and 9, and they're connected by an edge in the graph. So let's start with the baseline Markov random field approach. So this is the SEER. SEER would be the SEER implementation of the algorithm. So this algorithm takes as input the original image, the oversegmentation, and the number of output labels. In our case here, we have 2 labels. And the output is the final segmented image and the estimated parameters for the probability distributions for each label. So the first step is the initialization process. We initialize the parameters and the labels randomly. The second step is to create the graph from the oversegmentation, going through the process that I explained before. Then we have to find all the maximal clicks of the graph and construct the K neighborhoods for all maximal clicks. In our case, we use K as 1, and we obtain what we call the first neighborhoods. So as an example, take a look at the illustration here on the right, and suppose that we have this maximal click here represented by the red color. So basically the first neighborhood is gonna contain all the nodes that are neighbors of the nodes in this maximal click. And those nodes are represented here using the blue color. So our first neighborhood here would contain all the nodes represented by both the red color and the blue color. The next step is the optimization process itself. And for that, we use the framework called expectation maximization maximum a posteriori. And for that process, we have basically 2 main loops. One is for the EM iterations, and the other one is for the map iterations. And the map estimation is done for each neighborhood, for each first neighborhood of the graph. And then we have an update step, which is to update parameters and labels at the end of each EM iteration. Now let's take a look at the threads-based implementation. So this implementation uses the same input and parameters as the baseline implementation and actually performs the same types of computations. The computation is parallelized by dividing the N neighborhoods evenly across each of the T threads. So in this case, the first group of N by T neighborhoods is assigned to the first thread, the second group to the second thread, and so on and so forth. So the processing consists of optimizing a set of neighborhoods using maximum a posteriori and estimating the parameters for the desired labels, in our case, 2 classes. In this implementation, a shared memory array that holds results from the optimization process is used by all threads on subsequent EM iterations. And this shared memory array is a vector that carries the estimated classes for each node of the graph. So during the parallel optimization process, the threads are synchronized every time the shared memory is updated with the new estimated values for each node of the graph. So this threads-based model is a coarse-grained parallelism. So each thread is responsible for a rather sizable amount of work, which with little interaction between threads. Also, the way the algorithm distributes the work across threads does not take into account the size of the neighborhoods. So this can potentially lead to load imbalance, given that the neighborhoods can vary considerably depending on the input and the oversegmentation. Now we take a look at the OpenP-based implementation. As the threaded-based implementation, this one uses the same input and parameters as the baseline and also performs the same types of computations. On the other hand, this version is a finer grained version in terms of the workload distribution as compared to the threads-based version. So the inner loop of the algorithm iterates over neighborhoods, of which there are typically many, like thousands for 2D images or millions for 3D images. So we parallelize that neighborhood iteration loop using OpenP, and we use dynamic thread scheduling algorithm to achieve more even load balance across all threads. The challenge is that in this problem is that the amount of computation required for each neighborhood varies as a function of the size of the neighborhood and its connectivity to adjacent regions. So compared to the threads-based implementation, the OpenP design targets a finer granularity so as to achieve better load balance across threads. So one of the goals of our performance study is to better understand the performance impact of these different design choices. Finally, we have the VTKM DPP implementation. So in this case, this is a complete reformulation of the MRF algorithm using data parallel primitives. So to make use of the DPPs, the implementation actually recasts the algorithm into a sequence of DPP-based processing steps. So which means that we're using sequences of operations like scan, sort, and reduce. So if we take a look at the pseudocode here, for example, in line 4, where we see construct k neighborhoods from maximal clicks, this is actually, this process actually consists of several DPP operations, for example, a map operator, a scan operator, another map operator, and finally the sort by key and unique operators. So you can go through some more details in the full version of the paper, and also you can take a look in our previous implementation that describes the VTKM PMRF version. So there are several significant differences between VTKM and VTKM DPP implementation, the C++ OpenP, and the C++ threads implementation of this method. One of them is the level of granularity in parallelization. So the threads-based implementation is the coarsest decomposition. The OpenP would be in the middle, and the VTKM DPP is the finest level of granularity of parallelization. So each of the data parallel primitives is distributed in chunking fashion across each of the T available execution threads. Another main difference is also in terms of the size of the actual source code. I mean, we didn't actually count the number of lines, but we are going to see in the experiments, in the results that we obtained, that there is a significant difference in the number of instructions executed by each one of those implementations. For our experiments, we are trying to answer two main questions. The first one is, what are the key performance characteristics for each version? So basically, we're trying to figure out how well the different implementations perform on a single socket study. And the second question is, what are the factors that lead to these performance characteristics? So basically, we are collecting hardware performance counters to understand how well each implementation vectorizes and makes use of memory hierarchy. Going back to the data sets used for the experiments, again, we are using experimental data sets generated at the ALS beamline 832. And we use a geological sample that we are calling here sandstone. And we have two versions of that data set. One is sandstone 2K, with size 2K by 2K by 500. And the other one is Sandstone 5K, which has size 5K by 5K by 500. We are using two different platforms here. The first one is an Intel Xeon Phi. So Core is a Cray XC40 with more than 2,000 nodes containing two 2.3 gigahertz 16-core Intel Haswell processors. And it has 128 gigabytes of memory, and also has almost 10,000 nodes containing a single 68-core 1.5 gigahertz Intel Xeon Phi 7250. And those, they have 96 gigabytes of memory. The compiler that we use in this case is the Intel ICC compiler with this specific version. The other platform is an Ivy Bridge. So Island is an Intel Xeon CPU E5-2609 V2. And it has two 2.5 gigahertz 4-core Intel Xeon Ivy Bridge processors and 32 gigabytes of memory. And we also use the ICC, the Intel ICC compiler with a slight different version here. In terms of software environment, for the oversegmentation, we use a custom implementation of this leak algorithm. And for this algorithm, there are two main parameters, the superpixel size and compactness, and we use 80 and 10 respectively for each one of those parameters. For the C++ threads version, we use C++11 multi-threading for the parallelization. For the OpenP-based version, we use OpenP 4.5, taking advantage of the OpenP loop parallelism, constructs to achieve outer parallelism over MRF neighborhoods, and use dynamic scheduling. Finally, for the VTKM DPP version, we use the VTKM toolkit with API 1.3.0. Finally, for the performance counters, we are using the Liquid toolkit. We use the Liquid perf counters. And there are three sets of counters that we're using here. First, we use the total number of double precision scalar and vector instructions executed, and total number of all scalar and vector instructions executed. Then we have measures related to the L2 cache. For that, we have L2 request rate, miss rate, and miss ratio. Finally, we have the vectorization ratio. In the case of the Ivy Bridge platform, Liquid reports this directly. But on the case of the KNL platform, we compute this ratio to be V by the summation of V and S, where V is the count of vector or packed operations and S is the count of scalar operations. So the first set of results that we see here is related to performance and scalability. This is on the KNL platform. On the left, you see a plot for the 2K, the Sandstone 2K data, and on the right, you see the plot for the Sandstone 5K data. So for this set of results, the first thing we notice here is that for the VTKM DPP version, we see decreasing runtime up to around 32 cores. For the C++ threads version, we also see a decreasing runtime up to 32 cores, and after which point the runtime increases significantly. The C++ OpenP version presents better results, mostly likely because of the highly optimized OpenP loop parallelization. Those are results of scalability for the Ivy Bridge platform. And it's interesting because in this case, on the Ivy Bridge platform, all the implementations basically shows better scalability. And we believe that's because of the large L3 cache that's shared across all the cores in that case. Now we take a look at the hardware performance counters. So this table is related to the KNL platform. and I can point out or highlight some of the most important results in this case. So first of all, for this platform, we see a comparable vectorization ratios. So, going from 43 to 51%. In the case of the VTKM DPP version, as I mentioned before, we have a decrease in runtime up to 32 cores, along with an increase in the L2 cache miss ratio. And as I mentioned before, also the C++ threads version has a decrease in runtime up to 32 cores, and then the runtime increases significantly. Now in the case of the performance counters for the Ivy Bridge platform. So for the vectorization rate, in this case, we have a difference in results. So for the OpenMP and the threads-based version, we have around 70% of vectorization ratio. And for the VTKM DPP implementation, we have 18%. So we believe that the difference is because of the differences in the code itself, but also there is probably a variation in how the compiler auto vectorizes the code. So to summarize the experimental results that we see here, basically, in general, the VTKM, the DPP version is executing far fewer floating point instructions, which is leading to much better execution time. And we see this difference in vectorization ratio depending on the platform. So it's very clear that in the Ivy Bridge platform, there is a big difference in vectorization ratio. In terms of the scalability, again, we see a better scalability on the Ivy Bridge platform, but the thing is we only have 8 cores in that case, and maybe if we use more cores, that scalability is gonna change. But we believe that the main factor here is the large L3 cache that's shared across all the cores, as I mentioned before. So with that, I get to the conclusions and the future work coming from this paper. So basically, we now we better understand the performance characteristics of 3 different implementations for doing shared memory parallelization of probabilistic graphical model optimization code. And our goal is, in general, is to improve throughput of scientific analysis tools in light of increasing sensor detection resolution. And it was very interesting to see that, at the beginning of this study, we were expecting that the VTKM DPP implementation was running much faster because of better vectorization, but that's not true at all. It basically executes many fewer instructions. And we believe that this study that we present here is timely, shedding light on the performance characteristics of a non-trivial data-intensive code implemented with 3 different methodologies. And one of the future work that we are going to work on is basically pressing deeper into the topic of platform portability. And we're going to do so by going through the same type of study, now running those implementations on GPU. So we already can do that for the VTKM DPP implementation. That's one of the advantages about using VTKM. It basically just provides a way for you to run that implementation on GPU. But the OpenMP version also provides that capability. So we are working on the OpenMP version to emit GPU code. And that's going to be one of our future works, and that's in that direction. And I finished my presentation here. I would like to thank you very much for the organization, for the opportunity to present this work. And please feel free to contact me with questions at this email address, tperson@lbl.gov. Thank you so much.